Today I want to talk about neutrinos. They're fundamental particles, here they are on the standard model of particle physics, and they're created in the fusion reactions in the Sun, which gives out a colossal 10 to the 38 neutrinos every second. Then a massive 10 to the 29 pass right through the Earth every second, as if it's not there, and 300 trillion pass right through your body every second, which is why they are often referred to in mainstream media as ghost particles. Because so many pass through our bodies without us noticing, we definitely shouldn't be able to see them with our eyes, but I figured out that there's a very slight chance that one of them could hit an atom in your eyeball and cause a visible flash of light. The chance of this happening to you is very small, but because there's so many human eyeballs on the planet, roughly 10 people per hour on Earth will have a neutrino collide with one of their eyes. Now, nothing bad would happen, you'd just see a very faint flash of blue light. But I've never heard anyone talk about this before, even though, according to my calculations, it's true. Neutrinos are the weirdest particle in the standard model, and the ones we understand the least. There are 4 main reasons why they're weird. First of all, they're the only particles that only interact with other particles via the weak force. There are 4 forces in nature: gravity, electromagnetism, and the nuclear strong and weak forces. And the weak force is called weak because it's very short-ranged, which means that it's only felt by particles that are really, really close together, like 10 to the minus 18 meters apart. That's 1,000 times smaller than the nucleus of an atom, which is already incredibly small. This is why neutrinos go through your body as if it's not there, because to them, we just look like empty space. Technically, neutrinos also feel gravity, but they've got such tiny masses and gravity is so weak we can basically ignore it. In fact, that's the second weird thing about neutrinos. We've got no idea where they get their mass from. All the other particles with mass get their mass from the Higgs field, but neutrinos get theirs from somewhere else and we've got no idea where they get it from. Also, when neutrinos are flying through space, they morph from one kind to another. This is the only particle in the standard model that spontaneously changes into another particle. And finally, we've only ever seen left-handed neutrinos and right-handed antineutrinos. All other particles come in both left-handed or right-handed kinds of particle and antiparticle, but not neutrinos. For more information about all this, check out my video and poster on the standard model of particle physics. In fact, in case you are on the lookout for presents around now, I've got a load of educational posters available in my store, dosmaps.com, and I also have a range of kids' books for the youngsters covering space, physics, the human body, and the oceans. dosmaps.com, link in the description below. Anyway, like I said, neutrinos are weird and we don't understand them well because they rarely interact with anything. Despite them being the most abundant particle in the universe, we think there's even more neutrinos than there are photons of light. And even though neutrinos have incredibly small masses, less than 10 to the minus 37 kilograms, the combined mass of all the neutrinos is about the same as all the stars in the universe. So, to try and understand neutrinos, we've built a load of giant detectors underground to try and detect the very rare occasions where they do get close enough to collide with matter. This is what a neutrino detector looks like. This one's called Super-Kamiokande, and it's deep underground to stop any other particles getting through to it. It's a giant vat, 50,000 meters cubed of volume, filled with ultra-pure water, surrounded by photomultipliers, which are basically very sensitive cameras. Other neutrino detectors follow similar designs, but are filled with different kinds of liquid which absorb different energies of neutrinos. When a neutrino collides with one of the electrons in the liquid, the electron absorbs their energy and whizzes off through the liquid, giving out a special kind of light called Cherenkov radiation. Cherenkov radiation is kind of like a sonic boom, but for light, because the electrons travel faster than light does in the liquid. Which sounds weird because it sounds like I'm saying electrons travel faster than light. Well, yes, they do, but only because light slows down in a liquid. The electrons don't go faster than light in a vacuum, that's the thing that's impossible. But you can go faster than light if you slow down light enough, like in a liquid. And in that case, you'll emit this Cherenkov radiation. So with these massive vats of liquid, people are seeing the sporadic neutrino impacts collecting data and trying to figure out how neutrinos really work. Which is all good science and all that, but I was thinking these detectors look kind of like big eyes. If you think about it, our eyes are vats of liquid, and your retinas are sensitive to light, like the photomultipliers. So, if a neutrino hit an electron in your eye, would it also create Cherenkov radiation, and could you see it? Of course, our eyes are way smaller than these giant detectors, but we have a lot of eyes. So I tried to figure it all out with maths, and I also ran it past a professor of these things, and yeah, there's a very small chance a neutrino will collide with your eye gloop and create a flash of light. But this will only happen to you on average once every 89,000 years. So you'll probably never see one, but there are a lot of human eyes on Earth. In fact, if you collected all the human eyeballs on Earth right now, you could fill up Super-Kamiokande twice over. And that's why I love physics. Anyway, averaging all this out over the 7.7 billion people on Earth, we can expect around 10 people per hour will get a neutrino colliding with one of their eyeballs. But I hear you shout, how visible would this be? Would we even be able to see it? Well, our eyes are pretty sensitive to light. If you're in a dark room, you can register flashes of as little as 10 photons. And Cherenkov radiation from the neutrino impact creates around 200 visible photons per centimetre through the eye. 200 photons is way bigger than 10. So a neutrino impact would be visible, but only if you're in the dark because it would get swamped by daylight. Also, there are some subtleties with what angle the neutrino hits your eye and whether the cone of the Cherenkov light overlaps with your retina. I'm not an eyeball expert, so I don't really know how that would affect the statistics, but even if it's like 10 times lower, that's still one person an hour on Earth. We know that astronauts have seen light flashes inside their eyes when they travel outside the Earth's magnetosphere. These are thought to be caused by cosmic rays, but we don't really get this on Earth because we're mostly protected by the magnetosphere and the atmosphere. But still, some get through, so we might get flashes of light in our eyes caused by cosmic rays or even background radiation from the Earth. But I think it's very cool that if you see a random flash of blue light in your eye, you might be looking at the remnants of the most mysterious particle in the universe. Although I should mention that statistically it's much more likely to be a detached retina, so if it does keep happening, best to go see an ophthalmologist. Anyway, I'm genuinely interested to see if any of you have seen a faint blue flash in one of your eyes. If we get 90,000 people to watch this video, there's a good chance that one of you has seen this in the last year. So I'm interested to find out. Let me know in the comments below if that's happened to you. And if you want to learn the skills to do this kind of physics-based problem solving yourself, a fantastic place to start is Brilliant, who are sponsoring this part of the video. They're a website and app where you learn subjects in science and mathematics by actively solving problems. The thing I love about having learned physics is the toolkit it gives you to creatively figure out how to answer any strange question you might come up with, like, is it possible to see a neutrino? And to get good at this, you need lots of practice solving puzzles, and Brilliant is a fantastic place to do this and learn the fundamental concepts in physics at the same time. They have a wide selection of courses in physics going from quantum mechanics to relativity, and a whole load of other courses in mathematics and computer science with lots of interactive elements to play with. If you're interested, just go to brilliant.org/DOS, and if you're one of the first 200 people to sign up via that link, you'll get a 20% discount off your premium subscription, which unlocks all of their content. Thanks again for watching, and I'll see you in the next video.